Okay, I think we'll get started. Welcome, everyone. Thanks for joining this morning. Happy to introduce our CGD seminar speaker today, Tokarska. Dr. Tokarska is a postdoctoral researcher at the Institute for Atmospheric and Climate Science at ETH Zurich, working in Reto Knuti's group. Her work focuses on estimating remaining carbon budgets for the Paris Agreement target and quantifying related uncertainties. She also served as an expert reviewer of the IPCC special reports and is a contributing author to the upcoming IPCC AR6 report, in particular the chapter on constraining future warming projections. Kasia holds a PhD from the University of Victoria in Canada, where she worked with the CAN ESM model group, exploring carbon cycle responses in climate models of different complexities and different aspects of the carbon budgets framework. She also researched the role of negative emissions, as in artificial carbon dioxide removal from the atmosphere, on the reversibility of the Earth system, and the detection and attribution of anthropogenic climate change from the observed record. Today, she will speak about understanding and embracing uncertainties in the remaining carbon budget for the Paris Agreement target. Kasia, the floor is yours. Oh, you're still muted.
Thank you so much. Thank you so much for this invitation, and thanks so much for the nice introduction. Sorry, just to double check. Oh, okay. If I can share my screen again. Okay. All right. Can you see my screen right now? Well,
looks great.
All right, perfect. Right, let's get started. Thanks everyone for coming. It's a pleasure to be giving this talk, and I hope it will be highly interactive because I try to have some engagement questions throughout the talk, so please pay attention. I'm going to talk about the understanding and embracing uncertainties in the remaining carbon budget for the Paris Agreement target. But before we get started, I'd like to know how familiar are you with the concept of a remaining carbon budget? So I prepared a range of answers from I don't really know what it is and I never talk about it, to I have heated dinner conversations about remaining carbon budgets almost daily. So let's try out launching a Zoom poll. You should be able to see a pop-up window now and choose an answer that best represents your interest and knowledge in the remaining carbon budget. And this is anonymous, so we'll only see the statistics, but we don't see who voted for which answer. All right, I'll give you like a few more seconds to complete it. All right. Okay, so here you can see the results. So that's good to see that most of you have some understanding, but talk about the budgets infrequently. And some of you are quite new to the concept of the remaining carbon budget. Well, too bad no one has heated dinner conversations, because this is a really exciting concept. And I will hopefully get to convince you to talk about it more often, because it's a very interesting and important concept. Before we get started talking about the remaining carbon budget for the Paris Agreement target, I would like to clearly distinguish it from the global carbon cycle budget, which shows us the balance of the emissions that are being put into the atmosphere from anthropogenic activities and taken up naturally by the land and ocean carbon sinks. So for the past decade, 2010 to 2019, on average, we emitted about 9.6 gigatons of carbon every year from fossil fuels and industry, and about 1.6 gigatons of carbon per year from land use change. And our anthropogenic emissions, they go to the atmosphere, but about half of them get naturally absorbed by the land and ocean carbon sinks, and the other half remains in the atmosphere, which is the concerning part. So despite, as you probably know, it's a very highly nonlinear system, and there are nonlinear feedbacks between the atmosphere-ocean and atmosphere-land interactions, and they are both dependent on the atmospheric CO2 concentration as well as the temperature. So it's a highly nonlinear system with lots of different feedbacks, and it's not that easy to quantify them because sometimes they act into different opposing directions. So nevertheless, despite this complexity, if you plot global warming as a function of cumulative carbon emissions, you end up with approximately a straight line. And this is kind of the key concept behind the remaining carbon budgets, which we call this TCRE, or the transient climate response to cumulative carbon emissions. So if you like equations, basically what this TCRE line is it's defined originally as the CO2 induced warming. It's a function of cumulative emissions, and cumulative emissions, this would be the total emissions if you add up together the atmospheric carbon reservoir, land and ocean carbon reservoir. Or likewise, you can also just integrate in time our emission rate. And you have basically CO2 induced warming as a function of total emissions. You get approximately linear line. So this this concept is remarkably simple, but at the same time extremely useful, because it allows us to know approximately for 1.5 degree target, for example, how much CO2 can we emit in order not to exceed this 1.5 degree target. So based on this relationship, we can easily know the quantity of carbon, and that's where the idea of a total carbon budget and remaining carbon budget comes from. So given what we emitted right now, so we are somewhere here, we have the remaining budget, how much more potentially could we emit in order to stay within the 1.5 degree limit. So the remaining carbon budget is the remaining cumulative CO2 emissions to reach a given temperature target. And you could potentially run a climate model and estimate it, right? Because we have all those carbon sink reservoirs, we have temperatures, so we can estimate it for the future level of warming, such as 1.5 degree. So if you do that, you might end up with this number here shown by the study number 28. However, if you use slightly different setup, you might end up with this number, or you might end up with some other number in between. So these are the estimates of the remaining carbon budget by the different studies up to year 2019 that they were published. And as you can see, there's a high, large spread among those studies. So you could get answers as almost zero. So basically we're at 1.5 degree now and we cannot emit anything else, up to 1,000 gigatons of CO2 that still could be emitted if you're in this study. So that's not really satisfying because it's really large uncertainty depending how you calculate. For the 2 degree warming, that's even larger. So you can, again, have very large, wide range between how much carbon is remaining from the year 2018 onwards, like between less than 1,000 to about 2,000 gigatons of CO2. So in this perspective from Yuri Rogel and colleagues that was published in 2019, they try to put those numbers in context, like how can we better understand what's happening here? And how can we get a better idea of what is the remaining budget? Because this information 0 to 2,000 is not really helpful, like it means somewhere in between. So there is a band-aid solution. You could actually bring all those numbers much closer together. Like, so for example, here, the blue ones are closer and then the red ones are closer. So what they do, instead of calculating the total budget from the year 1850s until now, and then until 1.5 degree, we only calculated from the present day onward. So basically we do rebasing. Our baseline is present day baseline, and from present day onwards, how much we can emit. So the reason why those numbers are much closer together is because you have much less room for error. Since we are much closer now to 1.5 degree than we're in the year 1850, even if your carbon emissions, cumulative emissions maybe have ongoing error, you will accumulate much less of this error from now until 1.5 degrees, as opposed to if you use much longer time period. So it's basically a mathematical trick that makes those numbers closer together, which is very helpful to know. And that method was also used in the IPCC special report. So for the 50th percentile of the remaining carbon budget, they showed that there's about, on average, 480 gigatons of CO2 left for the 1.5 degree budget. However, like this estimate is a little larger than maybe previously accepted, because we have this kind of, we can use the information from present day baseline and have smaller error in going from present day until 1.5 degree, but it doesn't really address this root problem, like why those numbers are so different and how can we better understand this uncertainty and how can we have more confidence in what the remaining budget is. So there's still quite a lot of variation among the studies. It is a little better understood, but there's also a lot of room for exploration. So in this talk today, you will learn about the different sources of uncertainty in the remaining carbon budget. what are the different ways to tackle those uncertainties, and also how can we implement the concept of the remaining carbon budget into a real world setting. So this is a figure from the IPCC 1.5 degree special report from chapter 2, and it shows you those Tcre curves that I was talking about. So it's a warming as a function of cumulative carbon emissions. And you can see that for 1.5 degree target, well, there's not a single number. They kind of cite a range depending on the different levels of uncertainty. So the purple one is kind of the 33 to 67% range, but then you have like different levels of uncertainty, and the likely range would be in the middle of this star here. However, what is cited additionally, so the numbers I showed you are the ones here. This is the best estimate for 1.5 degree carbon budget, but there are also additional key uncertainties. And they provided an estimate of how much each source of uncertainty could contribute to difference of this remaining budget. So for example, if you are a very skeptical person, let's say, and like you assume the worst case scenario and all those uncertainties from non-CO2, scenario variation, non-CO2 response, and like additional Earth system feedbacks, if we assume they all act to reduce the remaining budget even further, so you basically add up all the most negative numbers here, you will end up with largely negative number, meaning that we already exceeded the budget if we kind of like think those all uncertainties are at the lower end of them. So the question we were asking here is, how can we use those kind of best estimates of the different uncertainties we have here, but how can we integrate them in this remaining budget estimate, so we can have a not only like the 50% chance of exceeding or meeting the target, but like also taking into account all the other sources of uncertainty. So if you think about it conceptually from this Tcre line I showed before, so the CO2-induced warming as a function of cumulative CO2 emissions is approximately linear, and it's approximately scenario independent, even for negative emission scenarios that was also shown recently. However, if we look at kind of the sensitivity of the carbon cycle response and the climate response, you could get a little bit of a tilt of this line. If we end up with, for example, very strong CO2 radiative saturation effect, then you're also going to get tilt of the line of this line, and other nonlinear feedbacks may also cause some additional tilts. Permafrost carbon feedback would tilt this line in the opposite direction, reducing the remaining budget amount, right? Because it would kind of cause additional warming. And then the largest source of uncertainty is this gray area here, which is due to the non-CO2 forcing. So here we have non-CO2 scenarios, and then also Earth system response to non-CO2 forcing. So these are the largest sources of uncertainty. And the reason why the Tcre line was for CO2 only emissions, and that was relatively simple, still subject to those kind of sensitivities. But once you add non-CO2 emissions, then you end up with much larger spread of where exactly this line should be in this spectrum in order to calculate the remaining budget. And our present day work conditions are such that there is both CO2 and non-CO2 forcing, and CO2 and non-CO2 emissions. We don't live in CO2 only worlds, right? So we are subject to all those different uncertainties. And how can we assess the remaining carbon budget given all those different sources of uncertainties? Well, so the first one approach you can take would be using climate models. So you can have a climate model, you can run it maybe several times for different scenarios to explore each of those different uncertainties, or most of them that we talked about, and see what's the remaining budget. So if you choose that option, we have 3 different sources of uncertainty related to climate modeling, which you're probably familiar with. It's the internal variability, uncertainty from model uncertainty using different models, and also scenario uncertainty. All right, so for 1.5 degree budget, so for 1.5 degree budget, which of those sources of uncertainty you think will be the largest? So I have another poll, so I'm going to launch it right now. And if we have internal variability, model uncertainty, and scenario uncertainty, or other sources of uncertainty, which one you think is the largest, considering we're talking about 1.5 degree budget? Okay, I'll give you a few more seconds to complete it. That's very interesting. Okay, all right. So I'm going to end the poll right now, and here you can see the results. So there's a slight preference that model uncertainty is the largest by 40%. However, 38%, so almost equal amount of people think scenario uncertainty is equally important, and internal variability, 22% of people think would be dominant. So hold on to this thought because we're going to explore those different options. All right, so let's start with the internal, with basically like looking at the climate model simulation and seeing what could be the impact. So first of all, I'm just showing you a single ensemble member from the CAN-ESM model, and that's run only once. And of course, if we want to explore internal variability, we can use a large ensemble. So here I'm showing the results for the 50-member ensemble of the CAN-ESM model. And the reason why we have kind of split here in the atmosphere ocean is because there's kind of 25 members for each of the slightly different ocean initial conditions, I think, but they could potentially be treated together as one large ensemble. But nevertheless, you can see that internal variability itself already introduces large uncertainty in those quantities that we are interested in order to calculate this remaining budget, because we need temperature and we need how much land and ocean are taking up carbon for the given emission scenario to calculate how much more we can emit. So also, if we add the models, then this further adds additional sources of uncertainty. And then we add different scenarios. So the top one was the SSP 2.45, but then if I use the SSP 585, I get quite different responses of the atmosphere land and atmosphere ocean flags. So we can see that all those things matter, and basically depending on which model, which scenario, which ensemble member you choose, you might end up with a different carbon budget, because if you add up those strings together and calculate the ratio, you might end up with completely different numbers. So one kind of mathematical trick again is that we're looking at the cumulative emissions. So if I look at the atmosphere land carbon flags and atmosphere ocean carbon flags integrated over time, because I'm interested in the reservoir change as opposed to the annual flags, it naturally smooths out because of the integration. So there's a slightly less uncertainty rather than here from internal variability. But nevertheless, especially on land, the models differ quite a lot in terms of the carbon sink uptake. Yeah, the question we had was those different options here: internal variability, model uncertainty, scenario uncertainty, or other sources. So let's now quantify exactly, or kind of by comparing them, how much they compare specifically for 1.5 degree carbon budget. And that was important part of this question because this is very near term. That's why all of them could be equally important. And specifically looking into internal variability first, I want to first add additional caveat, because with the definition of the Paris Agreement target, we're not really interested in exceeding 1.5 degree in a given year, because if we exceed it due to internal variability, but then the next year we don't exceed it and we go below 1.5 degree and then we exceed it again, that's very confusing, right? From the policymakers and from different perspectives. And so the interpretation of the Paris Agreement target is such that it's a long-term warming target, and therefore it should not be subject to internal variability. And it's also human-induced warming. So in principle, we should also kind of subtract the natural contribution to warming, but that makes very little difference. And therefore, we are interested in this red line as opposed to those orange lines. So that so first of all, internal variability does introduce source of uncertainty, but if we want to calculate temperature target for the Paris Agreement, we need to somehow remove this uncertainty from internal variability, because like we don't want to calculate budget for this and for this line, because this would be very confusing. So in order to assess like how can we kind of remove the internal variability, one way is to use the large ensemble. So here I'm showing the MPI large ensemble of 100 members, and we also applied polynomial smoothing in order to kind of smooth out this interannual variability. And then we have multi-ensemble mean of this 100 members shown in purple here. And if I zoom out this recent period here, you can still see, despite of the smoothing, we still get like some sort of uncertainty around this line. One of the ways of calculating the a kind of anthropogenic warming estimate that doesn't have internal variability nor natural forcing, is the Holstein et al. Method from 2017. And that's the one I think that has been broadly used in calculating this anthropogenic warming estimate. So what we did here, we did like kind of case study to use one single member from this ensemble I was using here. So the black one is basically randomly chosen MPI pseudo observations. So this is my MPI ensemble member that I treat as pseudo observations. And then to the black one, I applied this method of Holstein et al. In order to calculate how this anthropogenic warming estimate compares to the large ensemble estimate I got here. And it's more telling here on the zoomed in plot, where you can see that they are roughly very similar. So and the total uncertainty in that index is larger, but the uncertainty due to internal variability is the red one. And the large ensemble here, for example, for the MPI model, had slightly narrower range, but very similar. So overall, it seems like it's a good way of estimating this anthropogenic warming that would be more consistent with the definition of the Paris Agreement. Okay, so that's like for internal variability. So now let's look together internal variability. How does this compare to model uncertainty? So here I just plotted a spread of the different CMIC6 models that had multiple ensemble members available, and generally this is the plot you would get for this kind of effective TCRE line for the SSP scenario. And that's due to the model uncertainty. If we add internal variability, as you can expect, it's a much smaller contribution compared to the whole model spread. And if we plot the fractional contributions, well, if you're familiar with this sort of Saturn et al. Plots, we know that model uncertainty would be dominant. However, as some of you might have noticed, we are very interested in this very early part of the graph, especially that I use the present day baseline, or in this case, we're using 2011 baseline because we were comparing with other studies. So we're very much interested in the early part of the graph where the contribution from model uncertainty and internal variability are very similar. And if I zoom in that part, for 1.5 degree target, you can see that in this method, that's almost the same. So internal variability contributes as much to the uncertainty as the model spread for 1.5 degree target. And I'm sorry. And for the 2 degree target, the model uncertainty starts to dominate, but internal variability is still a large source of uncertainty. So that has to be addressed, both because of the uncertainty it causes and because in principle it's not relevant for the Paris Agreement target, but we're subject to it in the models and in the observed world, so we have to somehow account for it. So basically, if we use ESMs to calculate the remaining budget, well, you get like those different sources of uncertainty, and because we're looking at the 1.5 or 2 degree target from like some sort of present day or 2011 in this case period, baseline period, we get a bunch of different uncertainties that are kind of together acting, and it's really difficult to separate them. We could also do the smoothing and kind of calculate the ensemble means for each model with the larger ensemble. But again, early on for the 1.5 degree target in this graph here, you get quite a wide range, and it's not like a single number in this plot. And so is there another way of estimating the remaining carbon budget? Can we know? Actually, all right. So first of all, let's still look more into the scenario uncertainty. And as you could see on the previous plot, like even among the scenarios I was showing here, the SSP 2.45 is dotted, and then the 585 is solid line. So there is some difference between the scenarios, even because of the non-CO2 forcing, because due to CO2 only, this response should be basically pathway independent. So looking specifically into the scenario uncertainty, another problem we encounter is that the SSP scenarios, they don't span necessarily the whole scenario range that is relevant for the 1.5 and 2 degree target. So basically, these are the CMIC6 scenarios from the SSP kind of group. And as you can see here, there's the different warming levels. And if we're interested in the warming below 2 degrees, so this will be the scenarios that end up here. You can see that, first of all, some of them require quite a lot of negative emissions. And secondly, there's only a few of them that end up in those temperature ranges. And if we look into this emission spectrum only for this part of the graph, there could be a lot more possibilities. So in the 1.5 degree special report, the IPCC showed the kind of representative illustrative scenarios for reaching 1.5 degree and staying well below 2 degrees. And as you can see, there's like different levels of overshoot, even for the 1.5 or below 2 degrees target, right? So we could reduce emissions right away and then have very little negative emissions, or we could start reducing emissions slower and then reduce them more and have more negative emissions later on to offset it. In either way, in all those scenarios here, about the year 2050, you can see that they kind of cross the 0 line and become negative. So we have here the net negative emission part in order to offset the excess warming. So we don't consider, SSPs don't really capture this scenario space. So maybe also running climate models for each of those scenarios would not necessarily be the most useful thing to do, because there'll be like lots of computational resources needed to run it and for different models and different ensemble members. So is there another way? So another option, how we can estimate the remaining carbon budget, could be using the segmented framework. And what I mean by the segmented framework is we estimate each component of this budget separately and then kind of put them together. So this is kind of explained in this perspective from nature, and we have temperature limits. So this is our target, such as 1.5 degrees and remaining budget. So what are the different components of the budget that we could estimate, for example, from observations or from different lines of evidence and put them together? So we need historical level of warming in order to know where we are right now. So we have present day baseline, and that's subject to some uncertainty. And in fact, yeah, it could be plus minus 43% uncertainty in the remaining budget, depending how you estimate this warming. We need an estimate of the zero emissions committed warming. So the concept of the remaining budget is based on the fact that once we stop emitting, there won't be additional warming. And in case there is, we should kind of have an estimate for the zero emissions committed warming. I mean, it's usually, on average, it's actually estimated to be around 0, because some models show it's slightly positive, slightly negative, but on average it's 0. And it's often therefore assumed to be ineligible, and there are some studies that kind of explore those assumptions. And then we also need to estimate the additional warming due to non-CO2. So in the this is very dependent on the non-CO2 scenario variation between now and when we reach 1.5 degree. What's going to happen to non-CO2 forcing? Because if there's a lot of non-CO2 forcing from aerosols, for example, it might lead to additional cooling. But if it's lots of non-CO2 forcing from like methane, it's going to cause additional warming. And finally, we also interested in the Earth system response to forcing. So how does the Earth system respond to this non-CO2 forcing? And that's yet another source of uncertainty. So non-CO2 causes two sources of uncertainty. Firstly, what's the magnitude of the forcing itself or the emissions? And secondly, how much effect does it cause? How does the Earth system respond to that forcing? And then we have a TCRE distribution, which we can estimate from the models, or IPCC assessed using different lines of evidence. And there could be also observation in constraint TCRE, which I'm going to talk about a little later. So basically, we can estimate in this method every component of the remaining budget separately. And as a result, we still get the remaining budget estimate, but we don't rely on sole output from the climate models in order to assess it, which this approach is also subject to many different sources of uncertainty, but they are kind of distributed more among the different parts rather than just having like all the model bias and model uncertainty in one estimate. And finally, there's the permafrost carbon cycle feedback and other unrepresented carbon cycle feedbacks, or which we don't necessarily know how much they're going to contribute. So then again, there's some sort of estimates to further reduce the amount of remaining budget. And in this case, the reduction of the budget would be about 17%. And these are the numbers assessed from the 1.5 degree special report. So all those numbers are subject to uncertainty. And as you can notice, probably that uncertainty is going to be large, but that's because also the remaining budget for 1.5 degrees is very small. So that's why it's very sensitive to all your choices. And if your choices have very large uncertainty range, then they're going to affect your answer quite a lot. Sorry. Okay. All right. So what we did next is based on this approach. So this approach has been basically the underlying new approach that the 1.5 degree report used to estimate the remaining budget. And what we're going to do in the next few slides is to kind of building on this framework, we're going to introduce yet another framework, but it's also segmented like this, that each component is assessed separately. And we can put some observational constraints on some of those quantities in order to reduce the uncertainty in each of them, and therefore have a remaining budget estimate that integrates not only the values, but also the uncertainties around those values, and hopefully is more representative. But before we go there, there's a last question I have for you, which is, what do you think is the time that we have left before 1.5 degree is reached? And here the answers range from like, we have more than 20 years, 10 to 20 years, 5 to 10, 0 to 5, or less than 0, which means we already exceeded. All right, I'll give you a few more seconds to complete it. Okay, so it looks, I'll show the results right now. So it looks like majority of people, about 46%. I think it's about 10 to 20 years. And there are a few people, 5%, that think there's less than 0 years left. And then nobody, well, actually one person thinks there's more than 20 years left. So that's very interesting. And so to clarify, this question was actually not clear, right? Because it says how much time do we have left? But I guess the underlying assumption is if we continue emitting at the present day emission level. However, if our emissions decline drastically, we may never reach it. So then we have like a lot of time left because we never will reach it. So that actually was the tricky part of the question. And that's something we're going to explore in this next part of the presentation. It's like, what is this remaining budget given our observational evidence right now? And what's the uncertainty kind of hidden in this time between now and potentially reaching 1.5 degrees. And I just wanted to share here, okay, didn't really practice this, but let's see if this works. Can you see my browser or not?
We just see the hyperlink. We don't see the browser.
Okay. Maybe let's see if I can share it now. Okay. So there is this, you can see the browser now, right?
Yeah, looks
yeah.
great.
So this is the remaining budget estimate, and this is actually based on the study I'm going to show you. And if we play it again, I hope. Yeah. Okay. So you can see how so this is how much carbon we emitted from the year 1850 onwards, and it goes on. And here you can see our emission rate, and it goes up to the year 2020. And then here's the estimates of the 1.5 and the 2 degree budget. So basically, answering your question, how much time there's left? Well, basically, time is not part of this equation because we have this much piece of the pie left in the sense of the carbon budget pie. But how quickly we spend it, that really depends up to us. So I'm going to go back to the presentation. Okay, can you see the presentation back on?
Yes.
Yeah. All right. Yeah. Perfect. Thank you. All right. So yeah. So we have this much left here, but the time remaining, it depends how quickly we spend it, or maybe we will not spend it if we stop emissions tomorrow, for example. So that's quite a confusing, or I guess unclear question. So I'm glad the answers really showed that there are different ways of interpreting it. All right. So, but we still want to estimate where this place is. So how much carbon could be potentially emitted for this likely range, the 33 to 67% of the 1.5 remaining budget. So in order to do it, we introduce a new framework, which is also segmented framework, and there are 2 steps of it. So the first one is to estimate the TCRE, and then we take into account the uncertainties in the observable quantities in order to get a narrower estimate of TCRE. And secondly, we estimate the remaining carbon budget. So to estimate TCRE, we take basically 3 things into account. The human-induced warming rate, so that this anthropogenic warming index. So we can use observed warming estimates from like Hardcrude 3, Hardcrude 4 or 5. And then if you run this anthropogenic warming estimate, you're gonna get like how much anthropogenic warming is from the warming that we observe, and from other like the NOAA or the GACE data set as well. And we can have an estimate of the total historical CO2 emissions, which is based on the Global Carbon Project, how they assess how much CO2 has been emitted anthropogenic to the atmosphere and how much is taken up by the different reservoirs. And then we also have the fraction of the observed temperature increase that is caused by CO2 compared to the non-CO2 forcing. So this last, the FNC, we use climate model emulators such as the FAIR model to estimate this kind of fraction of radiative forcing due to CO2, CO2 to non-CO2 ratio. And then from there, we can estimate the remaining carbon budget. And these are results from our recent paper published here. So for TCRE, we have those three quantities: anthropogenic warming, cumulative emissions, and ratio of non-CO2 to CO2 forcing. And all of them have some sort of uncertainty around the best estimate. And that's why we can use, for example, Markov chain Monte Carlo sampling to sample across those different distributions to get a distribution of TCRE, because we're not interested in one single value, but we're interested in distribution. We also try doing a Bayesian approach, so kind of putting a flat prior on the TCRE, and then given the observational estimate or like the distributions from those parameters, what is the distribution of TCRE? But we basically got very similar results using either of those methods. So from here, once we have the TCRE, we can do like a little bit of reshuffling of the equations, and we can get similar way of estimating the remaining carbon budget. The only additional thing here would be that there's this FNC star, which is the future ratio of non-CO2 to CO2 forcing ratio. So here is our distribution of the remaining carbon budget, and it is shown here by this by this distribution. So if you assume that the emissions continue at the current rate and do not start declining, then we get about 6 to 11 years left at the kind of present day emission level. And another thing, what we can see here is that there is this gray area I showed here that the budget is less than 0. So even though you use observationally kind of informed quantities to calculate this budget, and this budget distribution is much narrow, is slightly narrower than the ones I showed before for IPCC, and much narrower if we kind of consider the budget across all the ESMs, we still get 1 in 6 chance that the budget has been already exceeded, because if it's negative, it means it was already exceeded. So the median remaining budget, or like somewhere, like the best estimate would be somewhere in the middle. So we still could potentially emit something, but it's not like, again, we are still subject to some of the uncertainties. And then we did sensitivity studies to how each of the assumption matters. So basically our main case is here, and then we, for example, doubled the uncertainty on each of the distributions, and we end up with the different kind of ranges. So what you can see here, the longest one is this one, which is related to this FNC parameter. So as we expect, the non-CO2 contribution at the present day and non-CO2 contribution in the future is the dominant source of uncertainty for the 1.5 degree budget, because it's relatively like near us, and it's also very small. And that's why your assumptions on the non-CO2 forcing matter a lot. And surprisingly, the uncertainty in the cumulative emissions actually doesn't really matter much. So even if we double the uncertainty in our cumulative emission estimate, they have less influence than the non-CO2 forcing. And yeah, we also try to estimate the non-CO2 forcing fraction and how it's changing over time. And you can see here that there is like this kind of almost approximately linear relationship between the kind of the present day, like 1990 to 2019 mean of the FNC, as opposed to the ratio of the non-CO2 forcing here. All right, so I think that's one of the last points I'm going to make in this topic here, which is kind of comparing the present day FNC, so this non-CO2 to CO2 ratio, to the future one. So we have the distribution of the future and the present day one, which is subject to all these uncertainties in aerosol, methane, and other non-CO2 emissions. And this also shows this approximately linear relationship kind of among those different combinations for different scenarios. So here we use the 1.5 degree special report scenarios that are consistent with 1.5 degrees target. And we run the FAIR model to calculate, to estimate what are those kind of fractions of each of those forcings for each of those scenarios. And yeah, if we put a line here with some sort of uncertainty, we can see that we could assume there's a kind of linear relationship approximately among them. So then we could calculate the remaining budget for the different combinations of those scenarios. And those isolines here show what is the remaining budget. So it could be minus 1,000 over here, but it could be very large if it's somewhere over here. So if then FNC is very high at present day and it's very low in the future, we could have very high remaining budget. But if FNC right now we're about where the star is, so FNC is like about here, and then this was our future estimate. But then again, if FNC star is very high in the future, we're gonna end up here, which is very low remaining budget. So it really shows that where we are right now and where we will be in the future is very much subject to the socioeconomic uncertainty, because that's related to the future non-CO2 emissions between now and 1.5 degrees if we reach it. So that's how we illustrate it in this figure. So our main case is the blue one. And then if we have a very high FNC star, it means the budget is going to be smaller. And if we have low FNC star in the future, the budget could be actually larger. So that's the main source of uncertainty. And here I compare it with the IPCC special report numbers, which is approximately kind of similar in our likely range here. As you can see, the blue one is narrower than the IPCC estimates here. And our range does account for those different sources of uncertainty because we kind of sampled it across the different distributions. So the conclusion is here that our choices really matter, because the non-CO2 forcing between now and the future is really important contributor to determining the remaining carbon budget. So the last few slides I'm going to show you is like the implications. We have much better now understanding of what is the remaining carbon budget and what are the main sources of uncertainty. But what does it really mean? Like, how is this relevant to the global global spectrum? So we have this perspective that we try to talk about the opportunities and challenges in using the remaining carbon budget to guide the climate policy. And this was the perspective led by Damon Matthews that showed up in Nature Geoscience later last year. And this is what we were talking so far about, is the global remaining carbon budget. But then how do we go from here to the national carbon budget district allocations, right? Because then one way to share this budget would be to kind of put some sort of share of the remaining budget to each of the country. And it turns out that this is really complicated task, right? Because it should be done in a fair way, which would account for the capability, equality, and responsibility principles. And in addition to it, not only we want to share this global budget among the countries, but also we would have to evaluate it for consistency if they actually add up together to what they could add up. Yeah, so there's a need for scientists to work together with both social scientists and policymakers to communicate the implications of the remaining carbon budget in a way that can improve and strengthen national climate policies. So basically, in a sense, we don't necessarily have to get the most accurate remaining carbon budget estimates, given how difficult it's going to be kind of transferring it between those two circles. But instead, carbon budget remain a really important concept that really can help strengthen the national policies in order to reduce the emissions and stop emissions eventually. And it's, of course, a sharing of the global budget among the different countries is subject to many value judgments. And there are the climate science components. So this is what we talk about, like what is the future warming contributions, radiative effects, additional feedback such as permafrost, the remaining to determine the climate carbon budget. So this is from the climate science part. But then, of course, there's all the other components such as value judgments, historical responsibility, different methods choices, that if you go from the global budget to remaining budget, you're also subject to all those different choices and assumptions, and how you actually go from here with the climate science informing this number to actually what really happens on the national level. So I'd like to show you how you can embrace this uncertainty. So carbon budgets are a guideline for setting climate policy targets. So we don't have to necessarily get the most accurate number, but it is still a very useful concept and could be used as a tool for mobilizing action towards emission reductions and reaching a net zero emission target in the long term, because we know that the implications are the same. So regardless of all those uncertainties and limitations of the TCRE, we know that we have to stop emissions in order to stop warming. And this really kind of shows us like what the sooner we stop it, the lower the temperature will be. And communicating kind of and understanding this concept, I think it's really important because people can get really stuck up on like getting the most accurate number. And actually, well, we're aware of the uncertainties, but that doesn't change really our overall conclusion, which means like we have to go stop emitting and reach a net zero emission level in order to stop warming. So the very final part of my talk is going to be about going towards this net zero world and net zero emission target. So then again, how conceptually you can use the carbon budget to reach the net zero emission target. And this is for 1.5 degree budget. So let's say from the present day emission level, if you have an idealized linear decline, you have a net zero emission target by the year 2040, you're still within the budget for 1.5 degrees. If, however, you decline at a lower rate and you reach net zero emissions on a global scale in the year 2060 on average, you will maybe be concentrated with the 2 degree budget, but above the 1.5 degree budget. And then if we continue kind of at the present day emission rate and the projected amount using the nationally determined contributions or the NDCs, we likely be over it. And therefore, there's like an overshoot budget that you have to remove it later with negative emissions in order to stabilize at the desired level of global warming. So at the time of the writing, this like current NDC pledges were insufficient to meet the Paris Agreement long-term target of stabilizing the temperature at well below 2 degrees. So therefore, just to conclude this talk, well, we know that we need to reach a net zero global emissions level to stop the warming. And the current NDC pledges are insufficient to meet the Paris Agreement target. So there's also challenges of the fair allocation of the remaining carbon budget among the individual countries, sectors, and industries. And this is a key priority to address. However, I would strongly recommend this approach to focusing on reaching net zero target emissions while staying within the given global carbon budget. So basically, like knowing how much we can emit, but the target is actually net zero emission target as opposed to our target is emitting all we can emit. So that's kind of changing the shift in the whole mindset of how we think about it. So I'll be really happy to answer any questions that you might have, but just before we go there, just a quick flag, we do have a special event in early May, and this is going to be a virtual talk on the reaching the net zero target with the science behind the net zero targets. And also we will have an interactive panel discussion with the very high level speakers. So you're most welcome to attend it. It's a virtual event on Zoom and it's free to register on Eventbrite. So you can just, if you write towards net zero world, you should be able to find it, or you can also find it by looking up my Twitter, which is my name and my last name. So hopefully some of you will be interested in joining it. And we also hope for interactive discussion during this event. All right, so back to the questions. I'll be really happy to answer any.
Thanks very much, Kasia, for that very interactive talk. I really appreciate that. So if you have questions, you can type them in the chat. I'm also going to put in the chat this link that Kasia shared to the spiral visualization, which I thought was really interesting, and I'm going to have to go back and spend some time looking at that. You can also raise your hand using the Zoom reactions feature, and it looks like we have a question from Anna, so go ahead.
Yeah, thanks, Katie, and thanks, Kasia, for this really great, engaging talk. So I was wondering, you constrained the remaining carbon budget with observations, and you also showed how much model uncertainty there was. So I was wondering whether there's any effort to constrain the models by using the models that are maybe closer to observations, so that meet some criteria, so that maybe you could reduce the uncertainty around the remaining carbon budget that way?
Yeah, that's a really good point. I think the way I try to kind of explain it in this talk, those two different approaches. So ESMs give us like one line of evidence and you can get the remaining budget estimate directly from it. And yes, you could potentially constrain both the temperature and the carbon cycle within the ESM itself, but that still might be subject to the structural model errors. And also this will be subject to whatever scenario you chose, right? Like the scenario uncertainty. And that's why, unless we have a whole suite of different scenarios, which are all consistent with the social economic assumptions between, like for the emission pathways 1.5 and 2 degrees, I think this will be quite challenging to do, as opposed to putting like using kind of observation based like global carbon budget like estimates how much we emitted until now, and what's the present day level of warming. And then we did make some assumptions about the non-CO2 forcing based on the climate model emulators. But yeah, like it definitely could be another approach. And I did try doing it before, like observation constraining warming and carbon emissions in ESM models. But because those models differ quite a bit, and I think the carbon cycle has quite a large uncertainty, it didn't really, like it didn't read too much narrower estimate than the one I was hoping for. So that's why I think personally this segmented framework is in a way leading to small uncertainties, because we can have narrower estimates of each component without the structural error from these ESMs.
Thank you.
Okay, there's a question in the chat from Simona. I'm going to read it. To the remaining climate warming, my understanding is that if we stop emissions right now, we are still going to warm the climate. One important factor is the projected reduction of aerosol emissions that will be reduced with reductions in fossil fuel. Can you explain why you think those factors do not matter?
That's okay. So this question is, just to make sure I understand this correctly, it refers to stopping. So if we stop emissions right now, what would be the expected change in warming, or if there is any? So it definitely is a good point. Like we assume that we stop emissions of both CO2 and non-CO2 emissions right now. And I think thinking about it, like stopping it tomorrow, it kind of makes it difficult to relate to. But thinking in terms of net zero targets, so like if we decrease CO2 emissions to a net zero level, and we decrease non-CO2 emissions either to net zero level, or we offset by negative emissions the additional warming things that they cause, the expected like the ZEC commitment or the zero emissions commitment is zero. So basically what we were referring to for the zero emissions commitment, we were like, if there were no emissions, like kind of we should not necessarily expect additional warming from the ocean thermal inertia, because it's being kind of opposed by the other kind of feedback in the climate system. And there is this zero emission commitment. It's CO2 only simulations, but they did the intercomparison among the different ESMs, and they found that it leads to a distribution which is centered on zero, and it's about plus minus 0.3 degrees for the, I think, 5 to 95% range, but I would have to double check that. So on average, it's expected to be zero. And I think the CO2 and non-CO2 contributions, of course, that really matters, the assumptions of it. But if we do reach net zero in terms of like not stopping emissions tomorrow, but like in terms of declining the emissions, I think both CO2 and non-CO2 would kind of be coupled and decline together. And once you reach net zero, you don't need to expect additional warming beyond that.
Maybe I can follow up real quickly. Hi, I'm Simone. I meant the effect of aerosols, really, the aerosol emissions, because right now you can expect that you have some kind of cooling through the aerosols, and that if those go away, you get an extra warming. Is that what you're taking into account as well?
To my understanding, in a kind of approach, yes, because we do make assumptions of what's that's why the FNC factor for the present day was already uncertain, and aerosols are the main uncertainty part. Yeah, so that we take that into account. But of course, if we had a narrower estimate of what's the present day aerosol forcing, that would really help us to have a narrower distribution of the budget.
Thanks.
Yeah, thanks for that clarification. I was also curious about the ZEC, the zero emissions commitment. So that helps in the sort of explanation there. I guess another question I had was about the negative emissions, especially because you worked on this topic and how they're very much relied on in some of the scenarios. So did you want to say a bit more about going forward, since we're getting closer and closer to 1.5 degrees C, how negative emissions should or could play into scenario design?
Yeah, that's a great question, and I can talk a long time about it because it's one of my favorite topics to talk about. So negative emissions, I think this is kind of the topic where people have very kind of extreme opinions, either like we should totally use it or not use it at all, but actually they are very helpful tool in aiding climate mitigation. So if there's some sort of emissions we cannot easily offset, they could be really useful for actually removing CO2 that we cannot easily reduce. So we could potentially reach a net zero emission level. That's why it's called not zero emission level, but it's called net zero emission level, where you could still have potential sources of CO2 emissions, but then you also have negative emissions to actually remove CO2 from the atmosphere. So in that sense, they are helpful in some of those scenarios. But of course, if you assume a very high overshoot scenario and then really large amount of emissions, negative emissions in the future, that's very problematic for many reasons, because you kind of like you just basically put the problem into the future, but you don't deal with it right now. And then there's also all these questions about the feasibility and the cost, because they are quite expensive technologies, and some of them are relatively safe, but while some other ones are kind of controversial in terms of like the ocean-based negative emissions, right, for example. So I think, I mean, there are choices like, for example, direct air capture, which is supposedly more expensive, but like it has very little impact other than just capturing CO2 from the atmosphere, or biomass combustion with carbon capture and storage. So that's actually not only like planting biomass, which I think the nature-based solutions are very maybe useful in the short term, but in the long term, if those trees happen to kind of, in a way be destroyed, either via climate change or by future human activities, that's a very short-term solution. But if we actually combust the biomass and capture the CO2, we have a net negative effect. So there are some solutions. I think the integrated assessment model people would be better people to ask exactly about the feasibility of it, but I think that's definitely something we shouldn't exclude, but at the same time we shouldn't put too much faith on it, because they are not a silver bullet. They are just kind of an aid towards the mitigation, but this does not mean that we should, like, the main efforts we should do like is to reduce emissions as much as we can.
Thanks. Peter, go ahead.
Thanks, that was a great talk, Kasia. I was wondering, you mentioned sort of the transient response versus the equilibrium response, and then there's model uncertainty as well. So you can get the similar transient response, but have very different equilibrium, like warming responses. So how do you sort of bring that together as well? Like, so you could have like if you've had a climate sensitivity that could be much larger, but have the same transient response through the historical period. So you'd have two models that are balancing out non-carbon versus carbon responses. Do you look at that element as well? Because I mean, if you can, I was just going back to Simone's point about if you just stopped emissions like today, and then you've got some committed amount of warming because you've got a radiant imbalance, the equilibrium sensitivity is going to be different for different models. Does that get included somehow?
So I think, okay, so there's two concepts. So I just would like to first separate it. So equilibrium response in terms of like ECS in the long-term response to warming. And so I didn't particularly talk about that, but I talked about the effective climate sensitivity, which is CO2 plus non-CO2 together. And then the TCRE, the original concept was CO2 emissions only. So what is shown actually is that TCRE and the carbon budget, like it's a very transient concept. So I have of course, for the ECS, like on the long-term time scales, there's like the nonlinear feedbacks and the pattern effect that matter. But looking on the transient time scales, I think like ECS is actually not easily correlated either with your emission commitment or with the, like it's only correlated with the TCRE metric through the TCR, which is the transient response. So I in order to avoid all those non-linearities between the present day and the future, assuming if we continue to warm, I rather just focus on the transient response alone, and then it becomes much simpler equation. So basically, the remaining carbon budget would be very sensitive to the TCR of the model. So what's the response to the doubling at the time of doubling of CO2, and also like what are the non-CO2 contributions from warming. And I think if we stop emissions, right, like if we go to the net zero and like we don't exceed the 1.5 degree level, I wouldn't worry necessarily about kind of the high ECS. I think that becomes a problem only in like the warming scenarios. But if we go to net zero and stop emissions, I think like this one paper of the Andrew McDougall and colleagues, they showed that there was very little correlation between ECS and zero emission commitment.
Great, thanks. I really appreciate that. It was a good perspective.
Okay, I don't see any other questions. We're at the top of the hour, so I think we'll conclude. Thanks very much, Kasia, for a great talk. Next week, we'll hear from Jerry Neal from NCAR CGD. So hope to see you then. And